Okay, so as I said, AlphaGeometry is a paper that I was very excited about when it came out because it's the first time I saw a very successful instantiation of the idea of having a symbolic engine doing most of the work and the model serving as something that resembles an intuition in some way. I pitched this idea to many people, and people disagree with me that this counts as intuition. So it's a but yeah, I like thinking with this intuition. So let's see what it means. So before we dive into anything machine learning related, let's talk about DD. DD stands for Deductive Database. It's a paper from quite a while ago, which was one of the, I wouldn't say one of the early papers in attempts to solve geometry automatically. I think that goes way back, but it's one of the ones that directly influences AlphaGeometry. The way the deductive database works is, first of all, they define, effectively the idea is to define a bunch of concepts such as points, circles, lines, angles, etc. Between those concepts, let me go slightly out of order. For those concepts, they define possible relationships, and then they have a database of what is called definite foreign clauses, which effectively say if certain statements are true, another statement is true, right? And so now what you can do is you can begin, like your problem statement is a set of statements, right? And then given your statements, you can use your database of those rules to construct a lot of other statements. And hopefully that will eventually lead to your to the actual solution to the problem you're trying to solve. And it has some caveats. One caveat is that a lot of rules involve negation, right? So like, for example, I say, hey, points A, B, P, Q lie on the same circle if two angles are the same, right, these two. And those 4 points are not on the same line. Because of 4 points on the same line, they're not on the circle, right? So there's a negation. That doesn't quite work with the definite Horn clauses because negation is usually not part of the statements you have. And they have, in the paper, they don't give a solution that work always. They have some heuristics that go around it. But some interesting things about DD, which DeepMind paper inherits. First one is that they use a concept of a full angle. So usually when you think of an angle, you're thinking of two rays, and the angle is the angle between them. Instead, they define angle as two lines and like an ordered set of lines, right? So the difference in this case is that these two lines can define 4 different angles, right? And but the definition just says, hey, the angle is those 2 lines. If you need a specific angle, you will have to specify something on top of those 2 lines, and that simplifies a lot of things. For example, you can say, well, 2 lines are parallel. A, B, and CD are parallel if and only if the angle ABPQ, all right, this 2 is equal to the angle CDPQ. If you were not using full angles, that would require, I think, 4 or 8 rules, right? Because if C and D are flipped, right, then the angle PEB would not be equal to angle PFD, right? So you have to, you would have to have multiple rules, but with full angles, it's just one. And they have a couple other examples. Even in this example that we used for the rules, you will notice that they say the angle PA, the angle between PA and PB is equal to the angle between QA and QB. But that is not sufficient rule, sufficient condition if you were using angles as 2 rays, because that angle could be AQB. APB. Yeah, you need to handle the separate case. I don't remember why. Anyway, it works. What's QAQB? It made more sense when I was preparing it. Anyway, full angles help. Okay. So the actual deductive database is a set of rules. There's 70 of them in the original database. You can find the old code base. The authors eventually created a product called, I think, JMax that has those rules, and you can solve problems and do things with them. So here's some examples. It says, hey, if E is a midpoint of AB and F is a midpoint of AC, then E, F, and BC are parallel, things like that. So on top of that, so if you just use DD, that can already solve quite a few problems. But there are two things that are missing. The first one still will involve no machine learning. One of them is that sometimes you need relationships between values, right? You can say, hey, the length of AB is equal, like is twice as large as some other segment or something like this. So for that, they introduce another concept called AR. I don't know what AR stands for, but effectively it's a way to introduce relationships between values, between scalars into the mix. So in this case, they have three examples at the end of the paper. Here I have one of them, where they say consider the problem. So the problem is on the left, and then they show the approach to solving it. And they first invoke DD, the deductive database. They say, hey, because we know that H is the X center, and because of that, they get three derivations. And then they say, because I is the in center, they get another three derivations. And so now that they have those, they switch into AR, where they can write down all the relationships and do algebraic inference, where they eventually conclude that VF is equal to CJ.
So is sort of like a markdown language for geometrical relationships.
So it's not necessarily, so it's not just, so AR is not aware of the geometric nature of the values. So for what you give to AR is multiple linear equations, like a system of linear equations, and it solves it for you and gives you new relationships between the values. And as a matter of fact, the way it works specifically is they build a matrix where columns are different values in your current state of the problem solution, right? So you will have like some angles, you will have some distances, you will have some ratios and whatnot, and the rows are relationships, right? So you might know that a particular segment is twice as large as another segment, or like if you have like 3 points on a line, you will know that the sum of the two of the lengths is equal to the third one, etc. So you write all of them down, and what you can do next is you can they run a Gaussian elimination, and that allows them to identify other relationships between those values, right? So in this case, they begin. They say things like, like let's say we know that a minus b is equals b minus c, right? So that means that if you move everything to the left, that would mean a minus 2b plus c is equal to 0, right? A minus 2b plus c is equal to 0. And then they have another one in the third one. So they write all three of them down. They do Gaussian elimination. They see that b is equal to d, right? That's something that deductive database would not give you, no matter how many rules you apply. But the Gaussian elimination allows you to get that. So then they put them together. So like in this example, we saw an example of where they would use DD and then AR. The way they put them together is they just run them one after another. So they run DD, they have a set of statements. They run DD and get all possible derivations from the database, right? So DD is very fast, and like there's never reason to apply any heuristic to running it. They just run it to completion until it finds everything that is to be found. Once they find everything that is to be found, they build that matrix run AR, which is effectively just solving a system of linear equations that finds new relationships. They put them into the set of all the statements, run DD again, and they repeat it until no new data is found. Okay.
Give me algebraic reasoning.
Oh, what the AR stands for? Yeah. Makes sense. Cool. Now, when you have DD plus AR, what is missing now is that when you solve a problem, sometimes you need to introduce a new point or construct something that does not follow from the existing things that you already have on your on the plane. Like, you can look at the circle. Maybe actually the next slide is an example. Yeah, so here's an example. That's problem from one of the IMOs. It says you have a triangle ABC, and there are arbitrary points D and E, which are equally far from A. And then you have, you construct BD and CE. Yeah, you look at these two segments, BD and CE, and you construct the perpendicular here. It is not drawn. And the intersection of it with the circle is points G and F. Right, and then they say, well, prove that DE is parallel to FG. It's a relatively hard problem. It's from IMO, right? And I have no idea how to solve it. But importantly, to solve it, what you need to do, starters, is you need to construct two more points, M and N, which are the point in the middle of the arc AB and the AC. Right, so you construct MN, and then once you have MN, you do a lot of inference, right? And eventually you prove that MN is parallel to DE and that it's parallel to GF, and from that you derive that the two lines that are necessary are parallel, right? Without being able to construct M and N, you wouldn't be able to solve the problem, no matter how many times you apply deductive database and algebraic reasoning, right? So. And the problem with auxiliary constructions is that deductive database, the number of rules is finite. Eventually, you will apply all the rules and get everything constructed. Gaussian elimination is obviously limited in time. It's n cubed in the number of variables, but the number of auxiliary constructions you can have is obviously unlimited. Right, because you can always construct another midpoint between N and C, and then midpoint between those two, etc. Right, there's no limit to how many auxiliary things you can introduce. Also, by the way, interesting thing here to notice is that they say angle CGN is equal to CAN, and if you look at CGN, and CAN, you will notice that they are not equal in the common sense. Right, because CGN is what is the opposite of acute? Obtuse, yes. While CAG is acute, right? But that is the reference to the fact that they use full angles. As full angles, they are equal. Okay, cool. So how do we do those constructions? This is where machine learning comes to aid. It will be a model that will be generating them. So the way it will work is they will run DD and AR until they have everything that is everything constructed that can be constructed. And once they run out of things that can be constructed symbolically, if they still haven't solved the problem, they go to the model and say, construct something new. And the model will propose a new construction. And it might be useless. If it's useless, that's fine, right? Because in the worst case, it will just introduce you, more things will appear that will not be used, right? But as long as after multiple invocations, the model does construct something you need, you will solve the problem. Now, the only problem is how do you teach the model to construct something useful? The number of problems solved by human is very small. It's like maybe in geometry, I think if we can get 10,000 problems, that will already be great. And they will not be of the complexity necessary to solve IMO. The way they do it is very interesting. They generate a very large synthetic data set, And the way they do that is they begin by proposing, just by constructing a bunch of random stuff, right? They will say, hey, we have two segments, AB and AC, and they equal. We have another point D, DB and DC are equal, and moreover, DB and C on the same line. If they're not on the same line, the first two statements can still be true, right? Like you can imagine if I pull D below, right, I would still have AB equal to AC and BD equal to DC, but it will not be on the same line. And then they start running so first of all, the way they construct it, it's not just random stuff. Instead, they construct one thing, or rather they might construct some random things, but then they have a set of rules which is designed to construct things that naturally appear in the existing problems, right? So this is separate from the deductive database. This is a database for constructing plausible constructions, right? So this is, I think, as far as they go in terms of human involvement into creating this data set. And so once they have those random things, they start applying DD and AR until they construct everything that can be constructed. And once they do that, they get a random statement. And now you have a problem. The problem says, given all of that, prove that this is true. But here you will notice that the fact that angle ABC is equal to angle BCA does not at all mention D, right? And therefore, everything that has D in it can be safely removed from the set of prerequisites, right? So in this case, the problem will say, given, so naively, if you just said, mention everything on top, prove the bottom, it would sound, triangle ABC has AB equals AC, and D is the midpoint of BC, prove that the angles are equal. But everything that involves point D can be dropped from the statement, right? So the problem can become the triangle ABC has AB equal AC, prove that the angles are equal. But to prove it, you do need point D, right? So that point D becomes this auxiliary construction, right? So that allows you to create a data set of auxiliary constructions. Interestingly, the actual data set, what it contains is givens, what needs to be proven, and then the whole proof, including all of the steps of deductive database and algebraic reasoning. And so effectively it would say application with deductive database rule, derivations from algebraic reasoning, and then some construction, more DD, more AR, construction, etc. And the model is trained to predict the whole sentence, not just auxiliary constructions, but also all the output of deductive database and AR, which are never used. The model is only used to sample constructions. Effectively, when they sample, they limit it to only being able to sample the construction, but according to their experiments, teaching the model to do the whole solution significantly improves our ability to construct. Presumably, it builds better model of the world. Okay, so this traceback where you want to get the smallest set of the statements, of the original statements, is not as trivial as it seems, right? It sounds just like, traverse the DAG, find everything that is that's a dependency, but it is not quite the case because it's not a DAG. It's a graph that has cycles because of the transitivity of multiple properties. And they mentioned 3. And I suspect this set of 3 is exhaustive, meaning that there's only 3 properties that introduce loops. One of them is equalities, and equalities is the easiest one, right? So here's an example. You might know that A is equal to B, B is equal to C, C is equal to D, A is equal to E, E is equal to D. You want to prove that A is equal to D. You can do it in 2 different ways. You can use the first 3, or you can use the last 2. The last 2 is smaller. But if you're just trying to do a backprop, right? If you just try to find all the dependencies, there are loops, right? Because depending in which order you started doing it, in order to prove that A is equal to D, like all 5 of them will be a dependency of yours. And the way they solve it for equality is relatively simple. They just say, well, once we know that A is equal to B and B is equal to C, we know that all of those things are equal to each other. right? So it doesn't make sense to keep them as 5 separate statements, which is going to have a single vertex in the whole graph that says all of those things are equal to each other, right? And then when you need to prove that A is equal to D, you can do like effectively within this vertex, you have a graph. So you know that all of those things are equal to each other. But the way you know it is by having those 5 edges. And then in that graph, you can do a BFS, right? In order to prove that A is equal to D, you might not know directly that A is equal to D, but you know that because they're in the same vertex, you know that you have a path in the graph between the vertices, where vertex is one of the scalars, and an edge is an equality that you do have a proof for, right? And you can use BFS to find the shortest path. That's going to be your smallest set. But okay, I don't have a slide for it. The other two problematic statements are collinear, right? So if you have a set of points which are collinear, like you know A, B, and C are on the same line, and then you know B, C, and D on the same line, then you know that all 4 are on the same line. It's a similar concept. The problem is that you cannot say, like obviously for any 2 points they are on the same line, right? So now you don't have edges between 2 vertices. Now you have hyper edges between 3 vertices, right? You will know that A, B, and C on the same line. You will know that B, C, D on the same line. And in a hypergraph with 3 edges, you cannot run BFS. Moreover, it's known to be an NP-complete problem to find such a shortest path. So they use some sort of a heuristic. And the last one is laying the same circle, where you need at least 4 points. So again, it's a hypergraph with the 4 edges. Similarly, they use a heuristic, like a best effort attempt to find the smallest subset. Okay, so that's for DD. For AR is interesting. You run Gaussian elimination, and you find a statement that B is equal to D, right? But in reality, in your Gaussian, like very deep into the proof, you will have 12 scalars and something like 10 to 15 equations, right? You run Gaussian elimination and you found that 2 of them are equal. So now you effectively used all 10 of them, but maybe you don't need all 10 of them. Maybe there's like 2 or 3 of them which is sufficient to prove it. How do you find them? The way they do that is they say, well, what we can do is we can present it as an attempt, like in order to prove that B is equal to D, you get each of those rows of the matrix, multiply them by some coefficient, add them up, and you want to get the statement B is equal to D, right? So in this case, what you would do is you would get, if I remember it right, you would get this one. Oh yeah, you just set x1 and x2 to 0.5 and add them up, right? So A's will cancel, C's will cancel, B will be -1, D will be 1, right? B is equal to D. So x1, x2 equal to 0.5 is the solution here. But you cannot just minimize the number of non-zero x's. That's not something that can be easily done. Instead, they represent it in a different way. They say instead of representing it as a single value, they will represent it as a difference of 2 numbers, each of which is non-negative. And then they try to minimize the sum of those non-negative numbers, such that multiplying this vector by this matrix gives you the statement you want, right? This is all they say. There are 2 problems with this. One is that, and they use integer linear programming. So there are 2 problems. One is that there's not always an integer solution. Moreover, in this particular case, the solution is not integer, right? It's 0.5 and 0.5, right? So I presume they're looking for an integer solution that gives you a multiple of the statement they're looking for.
These matrices will be extremely sparse, right?
Potentially, yeah. Which I guess linear programming can take advantage of. I don't know. The second problem here is that they are not minimizing the number of non-zero x's and y's. They minimize the sum of them, right? So here you will notice that if you don't need a particular row, the optimization will always choose x and y to be 0. So that's great. That's exactly what we want. If a row with a coefficient 1, then the minimal way to achieve that is to set x to 1, y to 0, which is exactly what we want. But the problem is that sometimes you might get two rows with coefficient 1, sorry, two rows with the coefficient 2, or one row with the coefficient 3, and then it will find you the wrong solution, right? Because 3 is smaller than 2 plus 2. Vice versa, right? But anyway, so it doesn't find you the smallest number of those values. So it finds you the smallest sum, which presumably in many cases will be close to what you want because coefficients usually will be around 1. Okay. Here's an example that puts all of those together. I don't even want to understand the problem statement, but it begins. So it says redundant for the constructions, but they're actually not redundant. It's just that you can't solve the problem without introducing them. But the solution that AlphaGeometry comes with actually does use them. So it uses K here, uses L. Effectively, it needs to prove that 2 points are symmetric relative to a particular line, and that line is defined without that auxiliary point, but it's harder to prove it that way. Anyway, so it begins by constructing 2 points from the model, and everything purple is DD. Green is also DD. This is AR, and then eventually it proves it. Right, so it's using all 3 components. Okay. Well, before we go to the results, one thing is when they measure it, they begin. So they assemble a data set, the test set. The test set has all the geometric problems from IMO going back all the way, I think, to 2000. I'm not sure. There was a total of, I think, like going back 10 years, or like 10 years. There was a total of, I think, 40, give or take, problems, of which some of them did not map into this paradigm. So what examples of problems that wouldn't map is any problem involving any inequality. Right? There's no inequalities in everything we just discussed. Or any problem involving combinatorics, because combinatorics is also out of scope. Right, so 30 of them did fit this paradigm. So 30 of them they converted. And then just using the deductive database can solve already 7 of them. Right, so I think even that is fascinating. Right, so out of 30 problems, just applying rules can solve 7. Then there's human design heuristics. They designed by the same person who introduced deductive database. He has a paper where he has a set of heuristics that introduce new points. So with those heuristics, they can solve 9. Right. So introducing algebraic reasoning brings it up to 14. And then they have an interesting data point. So they try GPT-4. They have a prompt that tries to solve problems. It solves 0, but then they say, well, it might solve 0 on itself. But what if we only use GPT-4 to construct auxiliary points the same way we use our model? That would be this. That gives you 1 more problem. So not massive advantage. But if they use human design heuristics, that brings to 18. And as a reference, it's not here in the table, but I think a gold medalist on average solved 26. Yeah, and AlphaGeometry solved 25. So that's a lot. It didn't solve 5, and they looked at some of them. I don't think I have slides for those, but I think some of them were completely out of reach. And for some of them, it needed, like it was missing constructing something, but if you introduce it, it would immediately solve it.
Is there a correlation between the problems that the humans can solve and the problems that AlphaGeometry can solve?
That I actually don't know. They might have mentioned it, but something interesting they mentioned is they looked at the number of people who solved the problem, right? So complexity of the problem and how long the proof of AlphaGeometry is. And they saw that for the 3 hardest problems, the 3 problems that were solved barely by anyone, the alpha geometry proofs are obscenely long, right? Something that is definitely not a human, human readable proof. But if you remove those three from consideration, then there is no correlation. Then it's, the proofs are not, the length of the proof is not correlating with the complexity of the problem. They also do a couple other things. So they have pre-training and they have fine-tuning. So during pre-training, they train on the whole proof, as I said, right? So including DD and AR. During fine-tuning, they only fine-tune on constructions, right? And so there's two more data points. One says, hey, what if we only train on constructing new stuff? Then it's only 21 problems, right? So interestingly, training on DD and AR is very beneficial, despite the fact that they never actually use the model to predict those. And without fine-tuning, they solve 23, right? So fine-tuning has smaller impact than training, than pre-training.
So what's the difference between the fine-tune model and the AlphaGeometry?
So AlphaGeometry, so this means they did pre-training and fine-tuning.
Yeah.
This one, they did only fine-tuning. Only fine-tuning meaning that they only trained on constructions. And this one is only pre-training, meaning they only trained on the full sequences, never only on constructions. And AlphaGeometry means they trained for a while on the full proof, and then at the end they fine-tuned when they only backprop the constructions, auxiliary constructions. Because they have a couple. I guess it's worth mentioning how they use it, how they use the system. The way the system is deployed is not like a single pass. It's not just DD construction, AR DD construction. In reality, it's a beam search, which with a relatively large beam size, where they explore multiple 512 solutions at a time. And they have a variety of ablation tests, not as many as one would wish, but quite a few. One says that you can train on a smaller data set. So the data set they trained on has 100 million proofs. Of those 100 million, I think only 10 million actually have an auxiliary construction, right? So 90 million fully can be solved with the DD and AR. Right, and if they only train on 80 million, or like all the way down to 40, they only lose 2 problems. And then they lose 2 more at 20, right? So it's so this point would be very interesting to know what happens when you train on more, right? Does it plateau at 25, or could you get it even smarter? So that's it would be nice to have. Because for DeepMind scaled, obviously they can train on 200 million. That's not a question.
It looks like linear, right?
But that's a very few data points, right? Like presumably it has to plateau at some point. You cannot solve more than 30.
I mean, it's not like between the bottom row, which is 20 million and another million, it's like a 5x data point. I think I don't have the number at the top of my head, but if you compare that with the same LLM standard scaling law, this is absolutely not there. There's no log relationship in there. So probably, yeah. I mean, if you, I would rather more be interested in what if we can increase the diversity of this data point and have more that require more construction instead of just 10 million out of them. And probably that's more impactful than just adding more of synthetic data. Just kind of my intuition there.
But it's still interesting to see if you train it on 1 billion, does it solve one more problem, or is 25 the limit?
Yeah, no. I see your point on like maximum, like is that the roof? But even if that's not the roof, as long as the scaling goal is linear, it's kind of okay. It's kind of not surprising. I think we are missing the exponential. The fact that the more problem you can see, the more capabilities it gets to solve problems. So I can shrink down the amount of data and I can increase the coverage of the LLM again. And that's what is missing from that table.
Yep. Okay. Table B is a different test set. It's a simpler problems from the people who created the deductive database. That was more like from local Olympiads or from textbooks. There's a total of 231. AlphaGeometry solved all but 3. Right. So effectively, it solved almost all of them. But it's worth mentioning that they relatively, like, deductive reasoning plus deductive database plus algebraic reasoning solved 198, right? So the data set is not particularly challenging. Yeah, the other two are related to beam search. Effectively, I don't understand deep search sufficiently deep, their implementation, to read those tables, to understand what they imply, but
Search stuff?
Hmm?
You mean by search stuff?
yeah, like what's the difference between the two? I think on the right one, for D, the beam size remains the same. It's always 512. Yeah. So one other important observation is that AlphaGeometry is open source, meaning that the whole code base is open. So you can see all the rules for deductive database that they use. They have some modifications to deductive database relative to the original one. You can see all the constructions, the beam search implementation, everything is open. Okay, this is the last slide. That's it for AlphaGeometry. They did publish another paper shortly after, not shortly, but after AlphaGeometry, called AlphaProof. We don't know much about that one, but they did expand to. So AlphaGeometry was very interesting because they did show that for geometry specifically, you can have a very good symbolic representation that captures a very large percentage of problems and in which you can solve them. But for more generic, for non-geometrical problems, it was not clear if that generalizes. And so they built AlphaProof is not using, they're not building their own domain-specific language anymore. They're using Lean, the Microsoft's formal verification language. And in Lean, on the last IMO, they solved 4 out of 6 problems, right? So they participated together with humans with the same time constraints, I think. Maybe not. And the 2 problems they didn't solve are both combinatorics. They don't solve combinatorics yet, right? So AlphaProof generalizes. One of the 4 was solved using AlphaGeometry. 3 were solved using AlphaProof. But AlphaProof, unfortunately, is neither open source nor the user paper, so we only know basics, which are effectively that, it's kind of similar. They're doing search in the space of Lean programs. But the dataset is not synthetic. The dataset is, the way they construct it is they get a very large number of existing math problems from Chinese Olympiads. There's 1 million problems that are transcribed into human language. And then they have an a somewhat unreliable converter from problem statement in natural language into problem statement in Lean, but they don't care if it's not 100% correct, because as long as the problem statement gets converted into something that can be solved, it's still a valuable data point, right? And then they run a lot of search to try to solve those. And solution would be a proof. In Lean, you have a statement, and then you have a proof. And if you prove the statement, the Lean program compiles. If you did not prove it, it doesn't compile, right? So the Lean program only compiles if every statement is proven, or if you explicitly bail out on proving them, but that is easy. You can say sorry. Sorry means, trust me, I'm a corgi, but you can easily check presence of sorries in your code base. Yeah, and so it's not a synthetic data set in terms of problems, but it is a synthetic data set when it comes to proofs. All the proofs are synthetically generated, and then they just train an LLM to predict those. And then they do beam search, which is beam search paired with the Lean parser, right? So beam search would only emit tokens that make sense. And at every point, I don't know how many of you played with Lean, but the way you do proofs in Lean is that you have one goal. Your goal is the problem you're trying to solve. And then as you go through the proof, you can you use so-called tactics, and the tactics change the goal in some way. Like, for example, you can have a very long, very large goal, and you can say, hey, it suffices to prove something else. And you provide a different statement. And now you have 2 goals. You need to prove that statement, because you say it suffices to prove it, well, then you have to prove it. And then you need to prove that given that, the whole goal is correct, right? So now you have 2 goals, right? And so the in the Lean program, if you like open it on GitHub, if someone uploaded a Lean program to GitHub, you will not see those goals as the tactics go. You will just see a set of tactics, right? But if you open it in an editor like Visual Studio Code, or they have an online one, and you like click into one of them, you will see the goals at that point, right? And so the alpha proof sees all the goals at every point, right? So it says, hey, this is my goals right now. What would be the next tactic to use? And it moves to the next one.
You mean like it reminds himself, like staying aligned to the.
Right. So as a human, you do the same. Like as a human, you wouldn't be just writing tactics, keeping in your head what's happening, right? You would be using Visual Studio Code, right? And you will see the tactics. Sorry, not the tactics, the goals, right? And then you use the tactic, and it updates it for you, right? So it's yeah. So the alpha proof model operates on the same environment as the human would. And generally, for those of you who did not use Lean, Lean is fascinating. It's super fun. And there is a thing called natural numbered game, which walks you through proving all the axioms about natural numbers, like, that addition is commutative, etc. in Lean, while teaching you Lean. And it's super fun. Every time you prove a theorem in Lean, it feels like the entropy of the universe reduced. And that's a good thing. Yeah. Cool. Yeah, we can conclude here.